Good morning. I thought I would create this video based upon the lectures in order that you can get some feedback on the slides 19 through 47, even though there have been fairly comprehensive videos on both the a priori and singular value decomposition work. So anyway, in terms of getting these ratings are very, very important. Clearly, the matrix that you've been seeing so far only has a small number of entries in it, and the more data we have, the more accurate we're likely to have in terms of being able to produce a model. But you've been able to see, presumably with singular value decomposition, that you can produce values anyway, and we can compress the matrix to a smaller number of dimensions in order possibly to improve or maybe make things worse. We'll see when I go over those slides very, very shortly. So the idea is that explicitly, if we can get numbers like 1 to 5, as we have seen with movies, that's awesome. But we can also infer information based upon the amount of time people spend on pages, whether they actually download something, whether after the download they actually use it, and so on. This whole process of engagement can actually be measured, and companies spend a lot of time actually creating software that captures these analytics in order that they can know where to focus their work for their business. The thing is that sometimes these implicit ratings may be difficult to know how accurate they are. For example, if you spend time on a page but don't move the cursor, well, you're actually there. The same if the tree falls in the forest, does anybody hear it kind of thing. Whether or not somebody actually purchased something or set up something for somebody else, these are problems. But very often what people will do they will actually then combine these particular things. So the cold start problem, knowing what to recommend for particular users, is a very real one. So we can actually ask somebody to rate some items, but there's only so far they can go. We can ask them some questions that are related to their demographic, and then use some kind of similarity to say, oh, this person is similar to this other person I have in the system. We'll use them, or we'll use some generic representative of a community, which is computed as some kind of cluster of users, all of whom have very similar properties. They like or dislike the same things. So in the next few slides, what we're going to talk about is this kind of neighborhood based algorithm. That neighborhood now is not necessarily anything beyond graphical neighborhood. And we're going to assume that if I move from one node in a graph to the next and then to the next, then probably the likelihood of information 2 steps away, it's less reliable than the 1 step away, that kind of thing. So the recursive collaborative filtering from Zhang and Pu from 2007 is quite simple. We look for a user who's similar to us if we want to compute a rating. Here the idea is we want to compute rating for item 5, but we don't know what that is, and so we want to find a user who's similar to us. User 1 we saw had a similarity of 0.85, so we can then ask the question, well, what would user 1's rating be for item 5? So we move to a neighbor and ask for their rating, and if they don't have a rating, we use some mechanism to compute it and then say whatever their rating was, we will use it for Alice. Very simple mechanism. So we're just going to predict it for user 1. A more elaborate mechanism is Huang and collaborators from 2004 is what we assume is that we're looking now for user 1 rating. We have this bipartite graph where the edges now represent the relation has rated. So you can see that user 1 has rated item 2 and item 4, but they haven't rated items 1 or 3, and therefore we really wouldn't know whether to recommend them or not. But what we would want to do is we would want to choose items 1 or item 3. What we're now going to do is to say, well, item 2 co-rated item 2, and item 1 was rated by item user 1 rated item 2, and so we could use user 2 their rating of item 3 to actually recommend that to user 1. So really what we're doing is traversing the graph and finding things with items which are a certain distance away from the original user. So here in this example we've gone from user 1 to item 2 to user 2 and then to item 3, and we're saying then that that three-step process allows us to recommend item 3 to user 1 by going distance 3, and then we could go distance 5 as a separate example. So here's the distance 3 calculation, and here's the distance 5 calculation that you can see. We've got to item 3, which has then taken us to user 3, which will then take us to item 5. So we would recommend item 3 before item 1 based purely upon distance. Other calculations we can do that you've looked at in the last few classes are singular value decomposition and the a priori algorithm that does shopping basket analysis based upon transactions. So I'm not going to spend too much time on those because you've already looked at them, but I will describe Bayesian and I will allude to clustering models, because clustering models allow us to compute a generic representative of a particular community, and you will use clustering in assignment 2 to presumably compute those communities of users that represent users who have common interests in terms of movies, both likes and dislikes. We're not going to talk about ever the pre-processing or the complexity of these particular algorithms, but suffice it to say that singular value decomposition is a much used algorithm in analyzing these kinds of systems and have provided a lot of good solutions and came to prominence during the Netflix competition in 2006-2007. The Sawar paper actually does discuss incremental updates, and I'll hopefully mention that again going forward. So the Sawar paper really looks at the sensitivity to accuracy with respect to starting with a small model and then adding models over time, which is a bit like the very small example which is in these slides a little bit further on. The idea is that singular value decomposition computes these latent factors which are talked about very much in the videos you should have watched, and hopefully you found them useful, and that those factors are to an extent representative of the domain. Like, they may not be explicit, but they are implicit in the data. They may not be called genre in the same way that when you analyze documents using LDA, the topics which are produced won't be named, fiction, non-fiction. They are labels simply that you associate, but we care as humans about the labels, but the machine doesn't care about the labels themselves. And the assumption in singular value decomposition is that by compressing the data, we squeeze out a lot of noise which is implicit in the ratings matrix itself. And the thousands by thousands size problem can very often be compressed with considerable efficiency or efficacy to 20 to 100 dimensions, which obviously makes real-time prediction very, very quick. So you will have seen this decomposition performed in the various videos, and that you will also have observed for Movie Lens, it's a very empty matrix. So go take a look at those videos associated with Lecture 20. What we're doing is we've got vectors that are ultimately produced which represent users, we've got vectors which represent items, but now they're using a coordinate space which are these latent features, but whether or not you call them a particular feature or something else, it doesn't matter. Ultimately, we are saying that a user has a vector representation in both the original space, i.e. the ratings for all of the items for Alice, or for an item, it's the ratings by all of the items in the original space, in the original matrix. In the compressed space, it's something different. It doesn't matter what you call those features, they are latent, they are hidden. What you're doing is you're decompressing, you're compressing, and then using, in this particular case, only 2 dimensions for the original matrix, which was 4 by 4. And if I take those submatrices from the original matrices U, S, and V, then I can actually find out what the overall predictions would be for the original matrix, where the original matrix was X, it's now X primed, and you could say by taking the norm of the difference of those 2 matrices, I can compute the overall error, and you'll find that the error in many cases for actual data where you know the actual ratings but you've hidden them from the original matrix is actually better in the reduced space than it is in the original space, because those unknowns are actually distorting the predictions. So the problem that's on these slides is actually, let's get Alice's prediction. We're going to use a submatrix which is complete in this particular case, which is nice. There's nothing unknown. So when we do the actual projection, we shouldn't have too much noise. This is the decomposition using JAMA. The projection would actually take these particular values from the original US and V. I can project Alice into 2 dimensions. The S2 minus 1 here is just a normalizing factor. I am choosing for both Alice 2D and item 5 2D projecting the matrix column or row into a normalized space so that I can project it, I can display it on 1 minus 1 there. So you can see it's projected into the same space, minus 1, 1, for both users and movies. That isn't to say they're the same things, they're not. It's just a convenience here, that's all. So one thing we can do is, when we've got these projections, we can actually perform some kind of calculation. And one way of doing it is to actually compute the projection using a matrix where I have removed the average for a particular user and then add on the average afterwards. So that prediction is the average for a user plus then the projection to 2 dimensions and then multiplied together to give me a particular scalar. And for the values on this particular slide, you should find that R, U, I for Alicia is approximately 2.5, 2.6 or so. So that's up to you to predict. But what I can do, and this isn't column 5, by the way, if you do that calculation of the projection for column 5, it'll give you something like 0.53 for approximately 0.53 minus 0.53 or something like that. So don't worry, it's not column 5. But we're assuming that we have an ability to project a movie into this reduced space to get an actual prediction. And so that's what's being done here, where if you decide to try and reproduce this particular value. So the mechanism for projection of prediction is to project for a new user, find the closest user and use her for prediction. For a new item, use it for prediction. Compute the that scalar and add the average to it for the user or item as appropriate, and then the matrix that you're dealing with is S minus the average. So that's a mechanism for a prediction. And if you use this kind of technique, you'll be able to compute all of the values in test through test 3 that are included on the course website. There are lots of ways of initializing the matrix itself so that you can just do an SVD. So fill up all of those -1 values, if you will. So you could fill them up with row and column averages, or both, or most frequent values, or a hybrid technique of the above. And then just do the projection for some value of k. And the belief is that for, let's say you've got thousands of users and thousands of items, by projecting into 20 dimensions, you'll get rid of all of the noise. You might want to do this for multiple initialization methods and then average the results. That might be a useful heuristic. There are many possibilities. Most frequent rating value, that's RF-REC, that we will talk about shortly in about 15 slides. This is just the projection, nothing more. So, SOA found that this can actually be pretty good, and the Netflix competition of 2006-2007 showed that these kinds of dimensionality reduction matrix factorization techniques are actually very valuable. There are other ways of actually moving recommendations from one domain to another, but they won't actually be discussed in this course. I do have an honours project. If you're interested, just contact me and I will send you that. Knowing what the right number of latent factors is, that's engineering. And you do a certain amount of trial and error, although the eigenvalues, which are essentially those scaling values inside of the S matrix, can be used to decide how many of them you want to use, as they represent, the trace represents all of the eigenvalues. So you could say, well, I'm going to use K to capture, let's say, 50% of the total trace or 75% of the total trace. That's what's done. But ultimately, experimentation is done to determine what K should be that works for your particular domain. There is no one right answer. So association rule mining, you will have seen the beer and diapers example extensively described in the slides. I strongly recommend you go through the annotations, the annotated slides, the animated slides, and convince yourself you know how to compute the frequent item set, because that is something that I consider the most important aspect of the a priori algorithm. But there are two components to association rule mining: the support, how many transactions, what percentage of the transactions does a particular set of items appear in, and then given a particular rule, how accurate is it, which is the confidence. So those two things are most important. There are other measures as well, like lift and so on, which are mentioned and described on the course website, but really support and confidence are the most important things. Hopefully the videos are provided a good explanation, and I'm not going to go over frequent item set support here. To use our ratings matrix to do association rule mining, then we just convert that matrix to a binary form where we replace a rating which is above the average by 1 and below the average by 0. And then we can actually mine it by seeing the number of records where I've got common ones and common zeros. So if we look at this particular case, then item 1 implying item 5, there's support of 4, where I've got both of these things in place. There are 4 records where I've got 2 and 5, and there are only 2 records where there are both of them in place, right? If you look, user 1, user 2 both have item 1 and item 5. The confidence in that rule actually is 100%, because when you've got 1 and 5 together, there are only 2 records, and they are both correct. You only include the records that don't include Alice there. So you can use this technique by running the a priori algorithm to come up with the frequent item set, and then the frequent item set is used to compute all possible decompositions of possible rules. Because obviously if I've got an item set here of item 1, item 5, there are 2 rules that can be produced. Item 1 implies item 5, or item 5 implies item 1. And generally the confidence of one rule will be better than the other one. In this particular case, it is no difference. It is no different. Item 1 implies item 5 in just the same way as item 5 implies. Oh no, item 1 implies item 5 is better than item 5 implies item 1. There is another way of looking at this ratings matrix and using it for prediction. And so what we want to do here is use Bayes' theorem. And what we want to ask the question is, how probable is the rating that we would give it the value 1 for item 5 given Alice's previous ratings? And those are all obviously the non-question marks in the matrix in the top row. So that's the conditional probability P of item 5 equals 1 given x, where x is Alice's previous ratings, with item 1 equals 1, item 2 equals 3, and item 3 equals, and so on. But we can use Bayes' theorem, which you can see stated below, and the right-hand formula assumes the independence of ratings, right? P of x sub I given y, as now where we've got the product over I, has replaced P of x, where I've got all of the items individually represented. So that independence assumption is kind of not that great, but it works quite well in practice. So we can do that kind of calculation for the ratings matrix, but what we can't do is actually compute the P of x, because we don't know what the probability of the set of ratings that Alice has so far, because we don't know that partition function. We don't know the probability of all possible rating sets. And that's okay, because what we're going to do is assume something right at the end, and we'll be golden. So let's look at the probability of Alice's item ratings given that item 5 equals 1. So if I were to say that, let's look at the probability given item 5 equals 1. Well, there are two records. And so the probability of item 1 equals 1, this first term in the product of probabilities, is 2 over 2, which gives me 1. The probability of item 2 equals 3 given item 5 equals 1 is 1 over 2, which is the second half. The third is what's the probability of item 3 equals 1 given item 5 equals 1. Because remember, we're only interested in these values that are represented in the vector x, which you see in the top right hand of this particular slide. So that's also 1 over 2. And then finally, what's the probability of item 4 being 2 given item 5 equals 1? So we can compute P of x for conditioned on a particular item 5 equals 1, and so on. We can do that for item 5 equals 2, 3, 4, and 5. Some of them are 1. And so we could actually then do the calculation for P of item 5 equals 1 given x, ignore P of x, because all we ultimately want to do is to rank these values. So P of item 5 equals 1 given x, P of item 5 equals 2 given x, P of item 5 equals 3 given x, and so on. And then we'll do the usual Bayesian thing that says, what's the maximum probability? And I'll choose that to be the rating. And so I would choose, given all of these P of item values equals y, the max value of that. And that would be what I would put in the question mark position in this particular matrix. So that's how I would use Bayes. Simple explanation here. There's a lot more to it if I want to use it in a practical system. And you can see that I may need to do some smoothing of the data, maybe even project into a lower level dimensional space, which is a kind of an interesting thing to potentially do. So project into a lower dimensional space, recompute the matrix now given that dimensional reduction, and then use those values to compute the probabilities, because those 0 or -1 values will now typically be changed to non-zero values. They'll be smoothed out, if you will. So very often we'll use combinations of these techniques. Never assume that we just use them one at a time, okay? So we can use clustering, and you will use clustering in assignment 2 to come up with users that have common characteristics. That's what we do. And in fact, those centroids of those clusters will actually be used as representatives, possibly to then use for new users. And we'll talk more about that when we do knowledge-based filtering recommendation next week. Slope 1 prediction. This is a nice, easy algorithm where basically we are saying that my trend is the same as the trend of a similar user. If you remember the chart earlier on in the slides where you saw two users, and even though their values were offset by quite large amounts, the trends in their recommendation, in their ratings, were just the same. So here what we're saying is that the value that Alice would have for a rating for item 5 is her rating for a particular user plus the slope, the differential slope that other people, similar users, have. So the slope for user 1 in going from item 1 to item 5 is 2 minus 1, which is 1, plus then the 2 that we are using, which gives us 3. And so our prediction for Alice would actually be 3. So what we do is we are going to perform this calculation across all of the differences of the co-ratings in order to make a prediction. So we look at all of those steps from one item to another in order to do the calculation. So here we've just got one user, one item to compare a slope for, but we can actually do it for all possible transitions in the matrix. So what we're doing is essentially finding a function that is an offset plus a difference which has a slope 1, right? The difference here is the difference of the two item ratings, and we're just assuming that the slope is 1. That's hence the name. And this is the Lamar and McLaughlin 2005 recommender. So we could use this as a way of initializing entries in the matrix, do SVD, and then do some kind of compression. That's another way of improving accuracy. So once again, SVD is quite an important technique, but what we might also use is these kinds of initialization techniques in conjunction. So this example is from Wikipedia. I strongly recommend you read it. It's a good example. It's got more slopes, and you can see that what we've got is a number of potential transitions. DNRs did not rate here. So what we've got is a number of transitions. If I were to compute for Lucy, then we can go from item B to item A. I can also go from item C to item A, and I can do these transitions in some cases for more than a single user. So you can see for item B to item A, I can do 2 transitions, one for Mark and one for John. But in the case of item C to item A, I've only got 1. Okay, so we compute the average. So in the case of the slope that we get from item B to item A, it's 5 minus 3 plus 3 minus 4, so we can have both negative and positive contributors, divide that by 2 in order to get the average slope, and then we can add in the slope from item C, but we need to bias the contribution of item B to item A by a factor of 2 because there are 2 contributors, John and Mark, whereas in the case of item C, there's only 1 contributor. And so that's why you see that the rating for Lucy would actually be 2 times 2.5 plus 1 times 8, all over 3, because there are 3 transitions, which gives us 13 over 3 or 4.33, which is quite reasonable. So this can take a lot of comparisons, but it's a very cheap calculation to perform. And slope 1 is used, as I say, as an initialization for SVD, then to do a compression to come up with improved ratings. RFREC is simpler still. All we do here is we look for the maximal frequency of a particular rating. So looking at the matrix that you see here. Alice, it has ratings as a row representative. Item 3 has ratings as a column representative. You can see that the maximal frequency is 4 and it is of the rating 1, and so that is the value that we put in as the rating for item 3 for Alice. That is the essence. This is another technique you could use to initialize your matrix and then perform SVD. Clearly I'm a big fan of singular value decomposition, and it's a very flexible and widely used technique. That's why I'm recommending it. The Gedikli, and collaborator paper of 2011 has some fine details on RFREC, but I expect you to understand the basic scheme in the form that I've just asked, and potentially be able to use it to initialize an SVD matrix, so you could do some form of compression. The way these things are assessed is using mean absolute error or root mean square error. So when I'm assessing my technique, what I'll do is I'll deliberately zero out part of that matrix, do the predictions using my technique, choose any of the aforementioned techniques, either individually or in combination, and then my prediction will actually be able to be assessed against the known rating, right? Because I've zeroed out an element, but I do actually have it. And so mean absolute error would take the absolute difference between the predictions and the ratings and sum it over all of the things that I've zeroed out, normalize it by the number of zeroed out items. And I would obviously be looking for my various techniques to compute an optimal or minimal value for that mean absolute error. Similarly, I can do RMSE, root mean square error, which is a slightly different calculation, and that's just places more of an emphasis on the actual deviation away from the mean. It really depends upon what's more important to you. So in the assessment, whenever you're doing some kind of summarization or assessment of your technique, you're performing some kind of prediction with respect to something that you have a known value. So the y value which you see in the summation there, and you can see the squared term is just to make sure that you understand that any error needs to be considered as something that I want to understand. I never want to just take the difference in value, because that could be positive or negative, and if it were positive or negative, then I could end up with a very bad system that had a zero aggregate measure, and that would be poor. I need to always include the absolute value or some kind of square, which we know to be positive. There are lots and lots of mechanisms that one can use for prediction. There are a good number which have been described in this slide pack, and you've actually played with in the previous classes, so hopefully you get a good grasp of what's going on. CF is a work in progress. That's all I can say. Very, very rich set of techniques. The thing is, it's an engineering task. You try these techniques, you try and get as much data as you can, encourage people to provide ratings, but that isn't always possible. Won't talk about multidimensional ratings. Here we've only talked about a single value, 5, as being a rating for a movie. We could easily make it 5 for the cinematography, 4 for the story, that kind of thing. So you could have a vector inside of that matrix as opposed to a single scalar value. We won't talk about that. Very often what is done is actually to create some kind of weighting associated with each and every rating that a user has provided, to reduce it once again to a scalar. So instead of 1 rating, 5 ratings, they get just weighted by certain values and then get reduced to another rating value. But there are other optimization techniques as well. The guide to data mining site's awesome. It actually talks about slope 1 and naive Bayes in more detail. Worth going to take a look at. The summary text here in Knowledge and Data Engineering is awesome. I suggest you take a look. There are more recent summaries, but this one's a very good one, and as far as you would need to go. It's not too long and worth scanning, if nothing else. Okay, thank you.